This video I'm going to discuss the fundamental theorem of calculus. This is a pretty important concept, so you may want to play over this one a few times or pause and think about things as we go. So we start with some formula, f of x, which I've just sketched here, just some curve. Now what we're concerned with is trying to find the area between this curve, the x-axis, between this point A and this point B. There can be any values. And we approach it like this. We imagine there is some new formula, capital F, which tells us the area from this point onwards. Now I'll illustrate what I mean. That's a bit of a difficult concept to grab. So at this point A, if I were to imagine a line vertically on top of this one, what would be the area starting from here? And we haven't moved yet, so that's a zero width, it would be nothing. So I'm going to graph this over here. This is my new formula. We don't know what the formula is yet. That's the whole purpose of this, this idea, is to find this. But at that point A, at the starting point, it would be zero area. What if we moved one step across? So the area between here and here, that'd be one, using these little squares, 1, 2, 2 and a bit. So 2 and a bit, that's probably about there somewhere. What if I move 2 steps across? The area starting from this point underneath my function is 1, 2, 3, 4, probably about 5. So that's 2, that's 4, there's 5 about there. So I'm stressing again, I don't know the rule for this, but it certainly looks like there's a rule starting to form. If I go 3 steps across, just counting squares, 1, 2, 3, 4, 5, 6, 7, that's probably about 8 by the time, 8 and a little tiny bit. So 2, 4, 6, 8 and a teeny tiny bit. 4 squares, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, combined that's probably 11, that's maybe 12. 2, 4, 6, 8, 10, 12. So I don't know exactly what this is, but it certainly looks like there would be some sort of a formula that would be describing where these points lie. And that formula is the unknown new function, capital F. So this is what we say. We define, or we let the area under here between from A onwards to be given by this new formula. We don't know what it is, but we'll just do a few little things to try and figure out what's going on. Now, in my original diagram here, I've marked off a point X just a little bit back from the end point B, and the width of this little tiny strip is H. So let's try and imagine how we would find the width of this little tiny strip H, just using this idea. Well, we know that this formula, capital F, is to give us the area starting from here across to some point. So the area just in this bit that I've cross-hatched from here to here, that would be my new formula if I substitute the value of x. That's exactly what we were doing counting squares. If I use my new formula and substitute all the way across here to point B, I'd get the area from here all the way to the end. Now if I take the area all the way to the end and subtract this first chunk, wouldn't I be left with this little strip here? So capital F of substitute B, subtract capital F substitute X, would leave that little tiny strip. B could be written as X plus this little step H. So F of X plus H minus F of X. That would give me the area just of the little strip. That's nice. Now, this little strip, we could come at this another way too. Imagine I took this point and just made a rectangle running across. Now I know that's less, but it's not too much less. That's only a little difference. And if h were small, that difference would be almost insignificant. Now what would be the height of this rectangle? Well, the height of that rectangle would be given by my formula, substituting the value of x. So if I do the height times the width, if I do f, that's little f of x, multiplied by h, that gives me the area of that rectangle, which is somewhat less than the area of the strip. That was f of x plus h minus capital F of x. But what if I didn't want an underestimate? What if I took this end point and made a rectangle here that's slightly higher, slightly bigger? Now it's bigger by this triangle, sort of a triangle, but it won't be too far off if h is small. So the area that I'd get this time, I'd be substituting in this value to my formula. Now this value is b, as we've seen b is x plus h. So that's little f of x plus h multiplied by the width h. That's the hard bit. Right there is the hard bit. Now I'm going to divide through by h. So f of x would be less than f of x plus h minus capital F of x, all divided by h, which would be less than f of x plus h. This thing should look familiar. That should look like taking a derivative by first principles. The only difference is we don't have a limit. Well, we sort of do. We said here that these discrepancies would be less and less if h were smaller. So really what we want to think about is what happens to this as h approaches 0. Nothing will happen to this. There's no h part. What will happen to this part as h approaches 0? Well, that will become closer and closer to just f of x. So this thing is in between f of x and f of x. Well, the squeeze theorem will tell us that this thing therefore would have to equal f of x. It's the same on both sides. So we can make this startling conclusion. The limit as h approaches 0 of this thing in the middle, capital F of x plus h minus capital F of x divided by h, must equal little f of x. In other words, the derivative of our function that we're trying to find equals f of x, the original formula that we had. Let me just say that again. The derivative with respect to x of the formula that we're trying to find, capital F, that's exactly what that is, that's the definition of derivative, equals little f of x, the formula that gave us our original curve. Well, what's the opposite of taking a derivative? An integral. So it would seem that we can find the formula for area if we take an integral of our function with respect to x. To make this more general, don't forget that we have to add a constant of integration. Now we can evaluate the constant of integration if we remember that we defined this originally to say we're starting from the point A. If I was to substitute point A here, I would expect this to come out to be an area of 0. Remember, this is the area under the function. That's exactly what this was defined to be. Area under the function is given by this formula, capital F. Well, if we did substitute A for this, and we wanted this to come out to be 0, could we see, I hope, so let's write this down, if x equals A, we know that the area must come to 0. So substituting into here, 0 for area, f of A plus c. I hope you can see that therefore the constant of integration is negative f of A. That works. Now I'll take this and I will substitute minus f of a into this point here. And I'll introduce a little bit of new notation. In general, we say this, that the area between the x-axis and a function between limits of a and b is equal to the integral, and we write the limits a and b on the integral of our original formula f of x integrated with respect to x. This gives us some primitive function, or antiderivative. Typically we write this in brackets and we copy our limits of integration a and b, and then we substitute the first one, f of b, subtract the second one, f of a, where really this minus f of a, it's the constant of integration from here. This is the fundamental theorem of calculus. This is the bit to commit to memory, and yeah, it takes a little bit of getting used to, but pretty much it tells us if we have some formula that's giving us a curve on a graph and we want to know the area under that curve between 2 points a and b, we take the antiderivative or the integral, substitute the limits, find the difference, and that gives us the area. Now in the next video I'll do some examples of this.